Hello, my name is Takayoshi Hachijo. I will start my presentation about this title. And the first topic is about our targets. As an implementation of autonomous civil construction work, we target soil eroding associated with sealed tunneling as shown in this figure. The soil excavated from the sealed tunnel is transported to an external soil pit via pipelines and conveyor belts, and then loaded into a dump truck by a backhoe and transported to a treatment plant. The backhoe operates depends on when the dump truck arrives, which in turn depends on traffic conditions. And this often causes waiting time for the backhoe operators. Therefore, automating these soil loading tasks would increase efficiency and productivity. Furthermore, in this case, the location of the backhoe, truck parking, and soil pit hardly ever change. We can install sensors in the environment to detect the shape of the earth mound in the soil pit and the position of the dump truck. This requires fewer sensors than in more dynamic situations, and this system is applicable even if the dump truck has no sensors of its own. For these reasons, our aims were to automate the soil loading involved in sealed tunneling and conduct demonstration experiments in the test field. In this paper, we give an overview of our system and the experiments performed in the test field. We use Opera to control autonomous construction machines. Developed by the PWRI in Japan, Opera is a research and development platform for automating earthworks. It contains a set of common control signals, middleware, simulators, a demonstration environment, and an autonomous construction machinery, and it is available on GitHub for open development. Moreover, Opera was developed in ROS2, which allows construction machinery and sensors to be controlled by common commands, independent of the manufacturer. We developed the measurement system by using multiple 3D lidars to detect the shape of the earth mound and the location of the dump truck. The resulting point cloud data enable accurate recognition of the shape of the target. And this allows a calculation of the best position for the backhoe to excavate more soil. We use ROS2 TMS for construction to manage the tasks of autonomous machinery. This task management system enables the accumulation and management of environmental information from sensors in construction sites and machinery. As shown in this figure, we place the three spheres in the scan range of all the lidars, and we estimate the center coordinates of each sphere from the obtained point cloud data. These figures show the cropped point cloud data around one of the spheres. Using points selected randomly from the cropped point cloud data of the sphere, we obtain its center coordinates. Next, we calculate the L2 norm between center coordinates and each point cloud data and counts the points for which the L2 norm is within threshold. This process is iterated 1,000 times, after which the length with most points is adapted. And we can estimate the sphere coordinates. We then place the prisms at a mechanically known point of the backhoe and the center positions of the spheres. The sphere coordinates in the world coordinate system were obtained by using a total station. We obtain the homogeneous transformation matrix and transform each LiDAR coordinate system into the world coordinate system. This figure shows the point cloud data transformed by the homogeneous transformation matrix. We estimate the excavation points from the sphere of the Earthman by using the point cloud data transformed by the world coordinate system. We extract the point cloud data in the soil pit and divide them into a planar grid. At each grid location, the lowest z coordinates is the height of the grid. And this grid data from the height map from which the highest grid points is estimated as being the excavation points. This movie shows the excavation by Backhoe, which avoided the pipes by preparing walls as obstacles in the simulation environments in advance. The backhoe waiting for the start flag of lost TMs for construction. The excavation task study. And the backhoe having subscribed the excavation points from the database. The backhoe executing the excavation task twice and the excavation the top of the Atma. We estimate the current position of the dump truck. We obtain the point cloud data of an empty dump truck in advance and find the coordinates at the four corners of the vessel. Ransack is used to derive the homogeneous transformation matrix that converts into the current point cloud data. And the points with the highest z coordinates give the height of the grid. And this grid data from the height. The purple rectangle is the estimated outline of the vessel, and the red sphere is the loading point at the relevant time. And the vessel is recognized when the variation value exceeds certain levels from the registration results. And the lowest point inside the vessel is estimated as the loading points in the height map in this rectangle. By performing coordinate transformation from the position and orientation of the vessel, it is possible to continuously estimate the position and orientation of the dump truck. This is conclusion. We have developed the 3D measurement system for autonomous construction. We configured the task of loading soil into a dump truck by an autonomous backhoe as the use case. And we conducted demonstration experiments of this task in the test field. I'm sorry that I cannot attend the great conference. I look forward to meeting everyone someday. And thank you very much for listening to the end. Thank you.